Hello there. Let's talk about the extremely important topic of least squares linear regression. Let's suppose that you work in the marketing department of some company and that you've collected some data relating the amount of money spent with advertisement per month and the revenue obtained in the same time frame. If you were to plot these data points, you might get a graph that looks like this one, which we usually refer to as a scatter plot. Now, let's suppose you'd like to know how much revenue you would get if you were to spend the amount of money shown here in blue. Well, we don't really have any data points at this exact amount of money, so you would have to estimate it somehow. You might, for example, take the average value of the two nearest known points. Or, if you need to be very conservative, you might attribute to it the smallest recorded value in the dataset. A very common strategy, however, is the following. Notice that there seems to be an upward trend in this graph. The more we spend in ads, the larger the revenue tends to be. So let's try to capture this trend by drawing a line that goes through the data points. And now, given this line, we can get our predicted revenue by reading its value off the y-axis, as shown in the picture. This seems like a reasonable thing to do, and this technique is known as linear regression. The line that we just drew is known as the regression line. Now, notice that there is one problem. How exactly do we choose our regression line? Here, for example, we have two choices, a green line and a red line. Both lines go through our data points and both capture the upward trend in our data. So which one should we pick? In this video, we will settle this question by using the so-called ordinary least squares method. Okay, so let's see how it works. Let's pick one of the points in our dataset and we'll call it point 1. This point has coordinates x1 and y1. Notice that the regression line predicts a different value for x1 than our observed value y1. We'll denote this predicted value by y1 hat. The hat is there to help us differentiate between the value we actually observed, y1, from the value predicted by the regression line, y1 hat. If our model were perfect, y1 and y1 hat would be equal. However, reality is pretty complicated, so in general, there is going to be a difference between these values. We'll call this difference the prediction error, and we'll denote it here as E1. Notice that we can calculate it by simply taking the difference between y1 and y1 hat. Okay, so that was all for point 1. We can do the same thing for point 2 and obtain its prediction error, E2. In fact, we could do it for all points in our dataset. Now here's an idea. Our regression line must be such that it is not too far away from any point in our dataset. In other words, if we want to choose a regression line, we must do it in a way such that the sums of the prediction errors is as low as possible. Seems pretty intuitive, doesn't it? Let's see if it works. Let S be the sum of all prediction errors. So S is equal to E1 plus E2 plus E3 and so on and so forth all the way up until E8. We can use the summation notation to make our expression a little bit more compact and a little bit easier to work with. As we've seen before, we can define our prediction error as the difference between the actual value y and our predicted value y hat. So let's substitute that in our formula for S. Notice that for point 1, y1 is greater than y1 hat since it sits above the regression line. For this reason, the prediction error E1 will be greater than 0. The opposite will happen to point 2. Since it sits below the regression line, its error will be negative. In fact, all points above the line will give positive errors, whereas all points below it will give negative errors. It turns out that this is a real problem. Our plan was to pick a line that made the sum of prediction errors as small as possible, and it turns out that's actually very easy to do. All we have to do is move our line upwards. If we do that, all errors will be negative, since they will all lie below the line, which will cause S to decrease. In fact, we can make s as small as we want. We just have to keep pushing our regression line up. So back to the drawing board. The problem with our approach was that we were summing numbers that sometimes were positive and sometimes were negative. So let's address that by getting rid of the negative values. A common way to do that is by summing the square of the prediction errors, as shown in the new formula. When we square a real number, we always get back a positive number, so this takes care of the negative values. There is even a nice geometrical interpretation to this approach. You can imagine that taking the square of the prediction error is equivalent to calculating the area of a square whose edge is equal to the difference between y1 and y1 hat. The total sum of the squared errors, therefore, will be equal to the total area of all these squares shown here in red. By the way, this idea of summing squares of errors is where least squares gets its name from. Notice that this solves the problem we had before. If our regression line lies too far away from our points, then the total sum of squared errors, here shown as the sum of the areas in red, will be very large. Okay, so that's what we'll do. Let's clear the screen and see if we can work out the math. We'll begin with our equation for the total sum of squared errors s. This is equivalent to saying that yi hat equals a times xi plus b for every point I. In this equation, two new variables show up, a and b. A and b are respectively the angular and linear coefficients of our line. Every pair of values, a and b, will correspond to a different line on the plane. Now let's recall that our goal was to find the line that minimizes the sum of the squared errors s. Our problem is, therefore, equivalent to finding the values a and b that minimize s. Okay, let's substitute yi hat in the original equation. This is what we get. Notice that s is now a function of a and b. We're now going to tweak these values to make s as small as possible. We know from calculus that when s is at a minimum, its derivatives with respect to a and b are both going to be 0. So let's write down the derivative of s with respect to a. We can move the derivative into the summation since the derivative is a linear operation. And using the chain rule, we arrive at this expression for ds dA. Now let's do the same for the derivative of s with respect to b. This is the expression that we get. As we said, at the minimum the derivatives will be 0, which simplifies our expressions. Let us now take the first expression and fully expand it. We'll get to this. Now we'll do the same with the second expression, and this is what we get. We can now break apart these summations, which will give us these new expressions. This is starting to look really messy. Let's give names to these summations to make our expressions a little bit more digestible. We'll represent each of the summations with these new mnemonic variables, s subscript the names of the variables over which they are summing. So, for example, the summation of xi times yi is going to be represented by s subscript xy. The summation of x is going to be represented by s subscript x, and so on. This last summation here is just summing the constant 1 for every point I in our dataset. The result of this summation is therefore going to be equal to the number of data points. Let's call it n. Substituting the new variables, our expressions get much easier to read. And we can further simplify them by canceling out the 2's in both equations. Finally, by rearranging the terms, we come to these expressions. Now here's something interesting. Given a dataset, it should be straightforward to determine its number of data points n. It should also be easy to calculate the sums sx2, sx, sxy, and sy. In other words, all we have left to do is find the values of a and b, which satisfy these two equations at the same time. That's not going to be a problem because luckily these equations compose a linear system of equations. And if we go ahead and solve them, these are the values of a and b that correspond to the least squares regression line. So okay, that was pretty abstract. Let's do a quick example and you'll see how easy it is to use the equations we have just found. Let's take the dataset shown in the table on the left. If we plot these values, we'll get the scatter plot shown in the graph. Let's bring over the equations that we just derived and place them over here for reference. We'll have to calculate these quantities here to get the values of a and b. N is simply the number of points. Here, n equals 8. Sx is the sum of our x values. Sy is the sum of our y values. Sxy is the sum of the products of x and y. So Sxy equals 1 times 2 plus 1.5 times 4 plus 2 times 0.7 and so on. Finally, Sx2 is the sum of the squares of x. Notice that first we square the numbers and only then we sum them. If you plug these values in the equations above for a and b, you will get these numbers. These are the least squares linear regression coefficients that we found. And here's the line that corresponds to them. I think it looks pretty reasonable. And that's it for today. Thank you very much for your time. If you liked this video, please consider liking it and subscribing to my channel. We'll be covering a lot more methods in the future. Also, hit the bell to be notified of my new videos. See you!